Alright, so I started solving a problem and I had to start over because there were some conflicting results. So let's see what is this problem about. We have a compound die press and it's driven by a motor that runs on average 1680 RPM, very close to 1750. That's a nominal, usually nameplate RPM of an asynchronous motor. The transmission ratio is 15:1, so we can calculate the RPM of the punch crank. The torque is given at the crank shaft. Coefficient of speed fluctuation is 0.02, consistent with what is in the notes. We need to calculate the energy to produce one punch. Okay, so energy per punch is going to be the area under this curve. It has a constant 100 value, and then on top of it there are the punch events, and the punch events happen between 120 150 once, and then happens again between 150 and 180. I made when I made the graph, I on purpose I made these points coinciding with divisions to make the analysis a bit easier. So what we need to get is the area under this this curve. We can do it several ways. We can define a piecewise continuous function. It will be like how many intervals? 1, 2, 3, 4, 5, 6. Too complicated. Equations of lines. We need to find coordinates of this point and this point. The other one is to calculate the area under the curve using graphics. So if you have graphing paper, or here using the rectangles, the grid, we can calculate that area. So let's see. I have one of these rectangles is between 200 and 400, so I have 200 times pi over 6. Pi over 6 is 30 degrees, so these are 30 degrees increments, okay? And then the vertical dimension of one of these squares, if the figure is faded, you can go to the back of the chapter and look at the actual figure. And so again, it's problem 5 at the back of the chapter 7. Okay, so what's the area of one of these triangles? It's going to be 200, so 400 minus 200, or 200 minus 0, 200. And then 30 degrees is pi over 6. Okay, and then I can count squares, and then I can add those squares and then multiply by the area of a square. And if I take radians, then the area of a square will be units of energy. So I have half squares, okay, half squares. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, this is a half a square. Or rectangle. They look square, but you know, units are different. Anyway, so half squares, I counted 12 once. And then I have here I have a triangle inscribed in a rectangle, okay? And because of that, I'm going to say that I have the number of squares here, or half squares, divided by 2. So there will be 3 half squares, or in terms of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 divided by 2, that's squares. And then I have 1.5 half squares here. That will be divided by 2. Let me split this into 2. Divided by 2. And then I have this other one, this bigger triangle, again delimited by the 100 line, 100 Newton meters line. So I have 1, 2, 3, 4, 5.5. 5.5 squares of 200 by pi over 6, and again divide by 2. Okay, so in total I have 12 plus 1.5 plus 5.5 equals, divided by 2, that's 9.5 squares. All right, so 9.5 times 200, that's 1900. So total area, it's 1900 times pi over 6. Okay, so again, 9.5 times 200. Okay, so one approach. The other approach is to work with a little bit more detailed without making use of the grid, that is. So I named this area 0, and it's area of this big rectangle, which is 100 by 2 pi. So area 0 is 100 times 2 pi, 200 pi. And I have the area of this triangle. Area of this triangle, it's going to be 400 minus 100 times pi over 6. Pi over 6 is 30 degrees again, from 120 to 150. Okay, so it will be 300 times pi over 6. Okay, and then the area of this other triangle, it's going to be 1200 minus 100 times pi over 6. So that's going to be 1100 times pi over 6. Okay, so if we add these two, we have 200. If I'm to multiply by pi over 6, so let me make this so that I have the same over 6. So I have 200 times 6. That's 1200 over 6 pi. Okay, so I have 1200 plus 300. 1200 plus 300 plus 1100 equals. Okay, I think I missed something. This is where the discrepancy is, and that's why I started re-recording. So what I missed here is to divide by 2 because I have triangles. Okay, sorry for this. So 1 over 2 because it's triangle, 1 over 2 because it's triangle. So this will be, it's good when you have concomitant methods so that you compare results, and if they're different, then you miss something somewhere. Okay, so it's 550. I think now I'm good. All right, so 1200 over 6, I'm not dividing, plus 150 plus 550 equals, so I have the same result as before. So this should be 150. I'm going to scan this, and you'll find it on Blackboard, this page. So 5. If you don't understand something, you can of course watch in detail. So total over 6. Okay, over 6 equals times pi equals 994.83. 994.83. You know what? I got this number earlier. I solved the problem before. So 994.8, 994.84 Newton meters. Okay. Now we're going to divide the total area to calculate the average torque now. So next we've got the total energy per one punch, and now we need to calculate the average torque. So the average torque is going to be the total energy, E total, that is 1900 pi over 6 divided by pi over 6 divided by the duration of a cycle and angle of crank rotation, that is 2 pi. Okay, so 1900 pi with pi goes away, so we have 1900 over 6 over 2, and this is 158.33. Okay, so a value that I got earlier. Okay, so average torque 158.33 Newton meters, and this is T average. E total, again 1900 over 6 pi, also confirm here using rectangles. Okay, all right, so we have the average torque. Now what we need to do is to draw that line on the graph. It's past the half distance between 100 and 200, and I'm going to use green color to draw the T average torque. All right, so the T average torque line. T average. Okay, T average. T average line intersects the curve 4 times. I'm telling it now. The delta E value that's considering sizing the flywheel, the one that's has units of energy, and it's exchanged with the flywheel, and we're going to use it to calculate equation what is it, 7.4. So that the delta E is going to be here of this triangle. You know, calculate here of this triangle, we need to, it's easy to find the height of the triangle. So height of the triangle is going to be 1200 minus T average, which is 158.33. But we need to calculate the value of the crank rotation. Let me call this delta theta. Okay, so how do we get delta theta? We can use trigonometry, similar triangle, sorry. So I can write this delta E over pi over 6, which is this interval. It's going to be the ratio, so I'm writing similar triangle. So you take delta theta and divide it by pi over 6. Pi over 6. And then this piece is going to be 1200 minus 158.33 over this full length, which is 1200 minus 100. Okay, so from here delta theta is what? So negative 158 plus 1200 plus 1200 equals over 1100 times pi over 6 equals 0.4958 radians. Okay, so now I can calculate delta E. I use green, it's this delta E. And this is going to be, it's a triangle, 1 over 2. I have the height. Okay, this height times delta theta. All right. So have delta theta in radians divided by 2 times parenthesis 1200 minus, I store in the memory 158.33 equals. So this is delta E, it's 258.25 Newton meters. All right. So now we can, so I have the energy exchange with the flywheel, and again, it's just the largest amount of energy exchange. I'm not taking the sum of what's above here. Also the small triangle, the first spike due to the first event. And again, the equation to use is 7.4, so use equation 7.4. And we have moment of inertia of the flywheel as delta E over coefficient of speed fluctuation times omega squared. Omega in radians per second of the crankshaft. Okay. So how do we get omega of crankshaft? It's going to be the RPM of the crankshaft, so it's motor RPM 1680 divided by transmission ratio, which is 15, and then it's going to be, so this is going to be RPM, it's times 2 pi over 60 or pi over 30. So 1680 over 15 equals times pi over 30. That's 11.7286 radians per second. The crank angular velocity. Okay. So I'm still having that in the memory. So it will be delta E again, 258.25 over coefficient of speed fluctuation is 0.2, and then 11.7286 squared. All right, I have this one ready, so I square it times 0.2 equals over 258.25 equals, and take the inverse. It's 9.3868 kilogram meter squared. And this is the answer. Okay, and this is at crankshaft. Not part of the problem, but we can easily calculate the required moment of inertia if the fly will be placed on the motor shaft. And in the notes I said that if you place on the motor shaft, it's going to be smaller by what amount? Transmission ratio squared times smaller. But by placing it on the motor shaft, the transmission between the crank and the flywheel could be gears there, belts, is going to experience all the overload, the pulses during the operation of the press. Okay, so what is the moment of inertia at motor shaft? This is equation that it's in the notes. It's equation either 3.9 or 4.3. So it's I at crank divided by transmission ratio squared. So 9.3868 over 15 squared. Over 15 equals, I have 0.0417 kilogram meters squared. And this is it. The solution to this problem. You saw two approaches: counting using the grid, or evaluating the area. It's some intersection to take care of, and if these curves, instead of being piecewise linear, you have higher order curves, you need to solve some equations. Say if this was were a parabola, you need to intersect that parabola with a line, sort of two sets of equations. Okay, so this was problem 5, chapter 7, and I'm going to post this on YouTube. It's on my cell phone. It takes forever to upload files from YouTube. Thank you for watching.